This is a Chapter 4 whiteboard lecture, Igneous Rock Textures, and covers PowerPoint slides number 3 through 24. In classifying the igneous rocks, we can break them down into two general categories, extrusive and intrusive. So these refer basically to categories of rocks that form above the surface. Those are extrusive or volcanic, so rocks are extrusive if they are formed from lava that has erupted from a volcano at the surface. And then we have intrusive rocks which form below the surface. So these rocks form when magma does not erupt but stays instead below the surface and very slowly cools down and crystallizes. So the word extrusive and the word volcanic are referring to the same thing. An extrusive rock is also a volcanic rock, and the same thing goes for intrusive and plutonic. Plutonic, by the way, comes from Pluto, god of the underworld, which can help you remember what that one means. This figure from your book is illustrating that same idea, that same concept. So we have the extrusive rocks that are right up here, and then the intrusive rocks are forming below ground. They've got examples over on the right of several different rocks that form. And then in the pink boxes, they give the texture of that rock. So we've got glassy rocks up here, pyroclastic rocks, and aphanitic rocks. Those are all extrusive rocks. Those are extrusive textures. And then we have porphyritic and phaneritic. Those are intrusive textures, so those rocks are plutonic or intrusive. In general, with classifying rocks, one of the things we look at is the composition of the rocks. And classifying just means to name. So the composition of the igneous rocks basically are those silicate minerals that we talked about before. And we can group those silicate minerals into two groups that have similar characteristics. So in our first group, we have olivine, pyroxene, amphibole, and biotite. These minerals are sometimes referred to as the ferromagnesian minerals. Ferro just meaning iron and magnesium meaning magnesium. All of these minerals contain iron and magnesium. Also, when you have a rock that's made mostly of these minerals, we refer to that as a mafic rock. And the same thing, mafic comes from the same two words, magnesium and ferro. Ferro, by the way, is the Latin word for ferrous, is the Latin word for iron. That's why the chemical symbol for iron is Fe. The second, I forgot about this slide, which has the photographs of these ferromagnesian minerals. So these are minerals that have iron and magnesium in them, and those two elements make the minerals dark in color. So we have olivine and pyroxene, amphibole, and biotite here, and all of them are dark in color, which is why we group them together. The composition of iron and magnesium gives them this dark color. And if you make a rock out of all of those ferromagnesian minerals, you end up with a rock that is also dark in color. So when we're identifying rocks, often just looking what we see visually can help us in classifying that rock. So the rest of the silicate minerals that we talked about are over here in this list: mustovite, plagioclase feldspar, potassium feldspar, and quartz. We don't have a word like ferromagnesian to refer to these minerals, but a rock that contains a lot of these minerals is referred to as a felsic rock, and that really comes from feldspar and silica. So these are all silicate minerals, and 2 out of the 4 here are feldspar, so we call those the felsic rocks. These are those light-colored minerals. Muscovite here, potassium feldspar, plagioclase feldspar, and quartz. Notice this distinctive pink color again. When you look at rocks that contain these minerals, you see that pink color showing up. So we can see it here, and we can see it in these minerals here that are in these coarser grained rocks. That pink mineral, very distinctive for a felsic rock. So again, if you see a rock that's very dark in color, it's most likely going to be a mafic rock. If you see a rock that has this pink color in it, it's going to be a felsic rock. So we're going to have 2 lectures on classifying the igneous rocks. This lecture is going to focus on the visual part of the texture, and then the next lecture will look at the composition. So for today, we're going to talk about how the size and arrangement of the crystals in a rock can vary and what that can tell us about the rock. So we're going to go through about 5 textures. And the first one is the phaneritic texture. This texture is made up of large crystals, so sometimes it's referred to as coarse grained. These are crystals that you can see without a microscope with your naked eye. Crystals like this form when magma has time to cool very slowly. So this means it has to cool below the surface where it's a little bit warmer. If you dig a hole down into the crust of the earth, it gets hotter and hotter the deeper you go. That's because there's heat at the center of the earth that is slowly leaking up toward the surface. So if a rock is cooling deep in the crust, it's cooling in a warmer environment than what we would experience here at the surface. So that slow cooling allows time for very large crystals to grow, and that slow cooling can take 10,000 or more years. So a magma could form and it won't actually become a solid rock for 10,000 years. That's how long it takes to completely crystallize. So rocks that form in this way are considered intrusive and plutonic. So the phaneritic texture is associated with intrusive and plutonic. This is an example of a phaneritic texture. Again, in this case, you can see the crystals with your eye. You don't need a microscope. You can see some potassium feldspar crystals in here. You can see some white crystals. The black crystals are a little bit smaller, but you can still make them out. So all of those can be seen without a microscope. The second texture is an aphanitic texture, and it's sort of the opposite of the phaneritic texture that we just covered. In this case, we have tiny crystals, and this texture is often referred to as fine-grained. In order to see the crystals here, you need a microscope. So you cannot see these with your naked eye. This is because the crystals don't have much time to crystallize, to build up into a large structure, because the magma has cooled quite quickly. And this is what happens when lavas erupt at the surface of the earth. So the environment at the surface of the earth is much, much cooler than the lava's temperature. And so the lava begins to cool quickly, and the crystals don't have time to grow into large crystals. So these rocks are extrusive and volcanic. So again, the aphanitic texture then is associated with extrusive and volcanic. Here are a couple of rocks with different chemical compositions that have aphanitic textures. So this rock over here is pretty dark. It's probably a mafic rock. This rock over here is got that distinctive pink color. It's a felsic rock, but they both have the same texture. They're both aphanitic, which means they're also both volcanic and extrusive. Just a quick comparison of the 2 textures. So again, phaneritic, you can see individual crystals with your eye. Aphanitic, you cannot. If you have to squint really hard to see crystals, then that's aphanitic. You don't need to do that. The next texture is a glassy textured rock. So this is just like the kind of glass you would see in window glass. We call this volcanic glass. The difference between a rock or a mineral and a glass is that the glass is amorphous. And amorphous is the opposite of having a crystalline structure. So remember, minerals have their atoms arranged in an order, whereas a glass does not. Sorry, not minerals. The atoms are arranged in an order, and that creates the crystalline structure of the mineral. But in an amorphous substance, the atoms are just arranged randomly. The reason that this happens is because the substance, the liquid, cooled very quickly. And that's true whether you're talking about window glass or volcanic glass. The way that you make glass is to quench it. You cool it really fast. So that's faster than just having the lava erupt at the surface. One of the ways where you make a lot of volcanic glass is when lava erupts out into very cold water, say on the seafloor. Then you get a very fast cooling that will create glass. One thing about a glassy texture is that the name of the rock does not depend on the composition. So normally to classify or name a rock, we need both a texture and a composition. But in this case, just the texture itself is enough, and any volcanic glass is called obsidian with a glassy texture. Another texture is the vesicular texture. A vesicle is an air-filled hole or cavity in a rock, and you can see those. There's a particularly large one right there. In both of these samples, we have holes or cavities. We refer to those as vesicles. So I've got two pictures here of two different rocks. They both have a vesicular texture, but they also both have a secondary texture. So pumice over here on the left is vesicular, but it's also glassy. And that means that if you looked under a microscope at the solid portion of the rock, the part that is not the holes, it would be a glass. It would not have any minerals or any crystal structure. But scoria, which is also known as vesicular basalt, is vesicular and aphanitic. So remember, aphanitic is that very fine-grained texture, microscopically small crystals. So if you looked at the solid part of this rock under a microscope, you would actually see crystals of different minerals. So they're both vesicular, but one is vesicular and glassy, and one is vesicular and aphanitic. Pumice, by the way, is very easy to identify because it has so many holes in it, so many vesicles that are filled with air, that it will actually float in water. There's more air than there is rock. The next is called a porphyritic texture, and this involves having a rock where there are two distinctly different crystal sizes. So you can identify large crystals and small crystals, usually microscopically small. The large crystals are called phenocrysts. So those are the ones that cooled slowly enough to grow large. So here is a phenocryst, this white crystal. And you can see other phenocrysts here and here, here. And then the ground mass is all of this area, all the black area in this rock here. This is all ground mass. And this is an area where cooling happens so quickly that the crystals could not grow large and are microscopically small. So we'll talk about how that happens in a moment, but first, just to name any rock that has this texture, regardless of what composition it is, we use the word porphyritic in front of the rock name, or we use the rock name and the word porphyry after it. So this picture is a porphyritic basalt or a basalt porphyry. Either of those are acceptable. Just two additional photographs of this texture. You can see how it can look different. For instance, the phenocrysts in this rock sample are much smaller The phenocrysts in this rock sample are much bigger and take up a lot of the volume of the rock. Up here, a lot of the volume of the rock is the gray ground mass. So how do we get a rock where some of the crystals cooled very slowly and some of them cooled very quickly? It's actually associated with the normal plumbing system of a volcano. So a volcano basically has a magma chamber at depth, and there are plenty of times during the volcano's history where it is not actively erupting. And during that time, that magma is sitting here below ground, slowly crystallizing because it's slowly cooling. There's nothing adding heat to it. The crust that surrounds it is cooler than the magma, and so it's slowly losing heat, and some minerals are crystallizing. Then at some point, there is a push. Maybe new magma gets brought up into the magma chamber from deeper. Then this magma erupts and it has these crystals in it. So the remaining magma would crystallize very quickly and create the ground mass that surrounds these large crystals that grew while the magma was sitting in the magma chamber. So that's how a porphyritic texture forms, and that's a common texture that we see in volcanic rocks because this is how volcanoes work. They operate this way. They have a magma chamber that sits for a long time underground, kind of slowly cooling down, and then something will happen that causes an eruption, and those crystals that have been growing slowly are brought up with the remaining magma. But that remaining magma then cools very quickly. The last texture is a pyroclastic texture, and this is associated only with volcanic rocks when you have an explosive eruption. So in this case, you end up with sort of broken pieces of rock that actually are all deposited together, and then those pieces kind of get cemented into a rock.